Have you ever looked at the graceful curve of a suspension bridge and wondered how engineers ensure it can withstand immense forces? Or considered how a business analyst can look at past sales data and confidently predict next quarter's profits? What about the technology in your favorite video game, which creates incredibly realistic movements and environments? These fields, engineering, business, and technology, all seem vastly different, yet they share a powerful hidden tool that makes their work possible. Believe it or not, the secret lies in a fundamental concept from algebra, polynomials. They are working quietly behind the scenes in all these scenarios and countless more. From the trajectory of a rocket to the coding of a roller coaster's path, polynomials provide the mathematical language to model, predict, and build the world around us. They are the essential building blocks for describing relationships that aren't just simple straight lines. Now, the word polynomial might sound intimidating, but the idea behind it is surprisingly straightforward. It's simply an expression built from variables like x or y, coefficients, the numbers in front of the variables, and exponents, all combined using addition, subtraction, and multiplication. Think of them as a versatile toolkit for mathematicians and scientists. But understanding their power starts with mastering the basics. That's exactly what we're going to do in this video. We're going to demystify polynomials completely. We'll break down the terminology step by step, making the language simple and clear. We'll walk through how to work with them, how to add, subtract, and multiply them with easy to follow examples. Most importantly, we'll keep connecting everything back to those real world applications, so you can see exactly how this math comes to life. Our goal is to take you from poly-what to feeling confident and capable. By the end of this video, you won't just know the definition of a polynomial, you'll have a true intuitive understanding of what they are, how they work, and why they are one of the most important concepts in all of mathematics. Welcome to the world of algebra. Today we're diving into one of its most fundamental building blocks, the polynomial. You'll see them everywhere in math, from basic equations to advanced calculus, and they're essential for modeling real-world scenarios in science and engineering. But what exactly are they? Let's break it down. The word polynomial itself gives us a clue. Poly means many, and nomial relates to terms. So, a polynomial is simply an expression with many terms. At its core, a polynomial is an algebraic expression made up of one or more parts, called terms, which are separated by addition or subtraction signs. To understand polynomials, we first need to understand the anatomy of a single term. Each term in a polynomial is built from three key ingredients. First, we have a number, which we call the coefficient. This is the numerical factor that multiplies the variable. In the term 7x, the 7x squared coefficient is 7. If you just see a variable like x, its coefficient is an implied one. Second, there's a variable. This is usually a letter like x or y that acts as a placeholder for a value that can change. And third, we have an exponent. This is the power the variable is raised to. Here's the most important rule for polynomials. The exponent must be a whole number. That means it can be 0, 1, 2, 3, and so on. But it cannot be negative or a fraction. Now let's put it all together and look at some examples of polynomials. An expression can be as simple as a single term. For instance, 3x is a polynomial. It has one term with a coefficient of 3, the variable x, and an implied exponent of 1. Here's one with two terms, x plus 5x, x squared plus 5x. The first term is x squared and the second term is 5x. Both follow the rules. And here's a longer one, 4z plus x, 7, 2x cubed minus 4x squared plus x, 7. This has four terms. Even the constant number minus 7 is a term. You can think of it as minus 7x, 7x to power 0, and since anything to the power of 0 is 1, it simplifies to just minus 7. It's just as important to know what isn't a polynomial. Remember that strict rule about exponents. It helps us identify expressions that don't qualify. Polynomials do not include variables in the denominator. An expression like 5 over x is not a polynomial because it's equivalent to 5x to the power of negative 1. Which brings us to our next exclusion, negative or fractional exponents. An expression isn't a polynomial if a variable has an exponent like minus 3 or 1/2. And finally, square roots of variables. The square root of x is the same as x to the power of 1/2, which, as we just learned, is a fractional exponent, so it's not allowed. So to recap, a polynomial is an expression made of terms, where each term consists of a coefficient and a variable raised to a whole number exponent. A term is a single part of an expression separated by addition or subtraction signs. For example, in 2x cubed plus 4x, 5 plus 2x, 2x cubed plus 4x minus 5 plus 2x, the terms are 2x cubed, 4x, and minus 5. Each term stands on its own. We classify polynomials by the number of terms. Monomial a polynomial with one-term example, 5x squared binomial a polynomial with two terms example, x plus 7 trinomial a polynomial with three terms example, x squared plus 3x plus 2, x squared plus 3x plus 2, polynomial any expression with one or more terms that follows polynomial rules. The coefficient is the numerical part of a term. In the term 6x squared, the coefficient is 6. The variable is x. The exponent is 2 coefficients tell us how many times the variable is being multiplied. The degree of a term is the power of the variable. Examples: 4x 1 cent degree term, 3x squared 2 10 degree term, 3x squared, 5x cubed 3 daddy degree term, 5x cubed. So our first degree linear, second degree quadratic, third degree cubic. The degree of a polynomial is the highest degree among all its terms. Example: 2x cubed plus 5x circumflex 2 plus x4, 2x cubed plus 5x squared plus x minus 4. The highest power is 3. So this is a 3-dot degree polynomial. Terms in a polynomial are usually arranged from highest degree to lowest degree. Example: 3x squared plus 2x plus 1, 3x squared plus 2x plus 1. This standard form makes polynomials easier to understand, compare, and work with. Have you ever wondered if the math you learn in school, like polynomials, has any use outside the classroom? The answer is a resounding yes. Polynomials aren't just abstract equations on a chalkboard. They are powerful tools that professionals use every single day to design, analyze, and predict the world around us. From the bridges we cross to the video games we play, these versatile expressions form the hidden mathematical backbone of modern life. They allow us to model complex relationships and turn abstract data into tangible, real-world solutions. Let's explore some of the most fascinating applications across different fields. Engineering in the world of civil engineering, safety and precision are paramount. Polynomials are fundamental in achieving both. Consider the graceful arc of a suspension bridge. That curve isn't just for aesthetics, it's a parabola which can be perfectly described by a quadratic polynomial. Engineers use these equations to calculate the exact length of suspension cables and to model the distribution of weight, ensuring the bridge can withstand immense forces like wind, traffic, and its own weight. The same principle applies to designing roads and roller coasters. To create smooth, safe transitions between straight sections and curves, Engineers use higher degree polynomials, often cubic polynomials. These ensure that the change in curvature is gradual, providing a comfortable and safe ride, whether you're in a car changing lanes on a highway or on a thrilling roller coaster loop. Beyond curves, polynomials are crucial for modeling structural strength. Mechanical engineers use them to analyze how beams and columns bend under stress. By creating a polynomial function that describes the load on a structure, they can pinpoint the areas of maximum stress and potential failure. This allows them to reinforce designs and build safer buildings, aircraft, and machinery. Business and finance. In business and finance, making accurate predictions is the key to success. Companies rely on polynomials to model complex financial scenarios and make informed decisions. For instance, a business can model its revenue with one polynomial function and its costs with another. By analyzing these two equations together, they can determine the break-even points where cost equals revenue and, more importantly, identify the production level that will generate the maximum possible profit. Financial analysts also use polynomial regression to analyze market trends and forecast stock prices. While simple linear models can show a general trend, the real world is more complex. A polynomial model can capture the nuanced peaks and troughs in a company's growth, providing a more accurate picture of its performance and helping investors predict future movements. This allows for a more sophisticated risk assessment and strategic investment planning. Science and technology are perhaps where polynomials are most deeply embedded. In physics, the motion of a falling object or a projectile is described by a simple quadratic polynomial. This equation allows us to calculate an object's height at any given time, its maximum altitude, and when it will hit the ground. It's the foundation of everything from ballistics to orbital mechanics. In the digital realm, polynomials are the artists behind the curtain. In computer graphics, smooth, organic shapes are created using something called Bezier curves, which are defined by polynomial functions. Every time you see a beautifully rendered curve in a font, a logo, or a 3D animated character, you're seeing polynomials at work, defining the shape point by point. Furthermore, in data science and machine learning, polynomial regression is a vital tool for modeling complex, non-linear relationships in data. Scientists use these models to forecast weather patterns, analyze medical data to predict disease outbreaks, and create algorithms that can recognize patterns far too complex for the human eye to see. Everyday life, you don't have to be an engineer or a data scientist to use polynomials. They pop up in everyday life more often than you might think. Anytime you calculate the area of a room or a garden, you're often using a simple polynomial. For example, if you're planning a rectangular garden where one side is 5 feet longer than the other, the area can be expressed as the polynomial a equals x times the quantity x plus 5, or x squared plus 5x. This helps you calculate the amount of soil or fencing you need, from optimizing a budget to even planning the timing of a road trip based on varying speeds. The logic of polynomials helps us make sense of and organize the world. Learning polynomials builds strong algebra foundations, prepares you for higher mathematics, improves logical and problem-solving skills, opens doors to careers in STEM, finance, and technology. Polynomials are not just math, they are tools for thinking. If this lesson helped you understand polynomials better, like this video, share it, and subscribe for more clear and practical math lessons. Drop a comment below and tell me
which part of polynomials was most helpful for you today.
Keep learning, keep growing, and remember, math becomes powerful when you understand it.